Well, thank you. So first, let me thank Matthias, Roman, and also Sebastian for organizing this wonderful workshop. This is my favorite, conference. I always want to come whenever I have a chance. I also try to bring my student here, who actually tell me we should relocate my entire group to Cargese. Okay. So during my talk, please feel free to interrupt me at any time if you have any questions, okay? Don't wait until the end. It doesn't matter whether I go to the end of my talk or not, but it's important we have this kind of interactions. And also, I would like to have tough questions, okay? That's what I expect from you and also especially from students, okay? So today I'm going to talk about physics and application of complex lasers. So let me first try to explain what do I mean by complex lasers. So there are many different definitions. So here's my definition, is that we consider the laser contains numerous lasing modes. There are many, many lasing modes, and they interact non-linearly with the gain material. So you can consider this is a highly, non-linear dynamic systems. And also, it has a high-dimensional phase space with complicated landscape. And because of that, such a laser can be in many different states and also display many distinct behaviors. So let me just give you a few examples. The first one is a random laser. It can laser either in a single mode or multiple modes. This actually is work done by Patrick Siba and Soan Jagan. They show that by changing the spatial profile of the pump, they actually can select the lasing modes for the same system. So you can really tell the system which frequency to lase, okay? Because the system has many frequencies they can lase. In addition to the spectral control, there's also work by Li Hong Wang's group showing they can also timing the dynamics of a multi-mode fiber laser. They can make the laser produce either continuous wave or pulses through the mode locking. And this also the output beam profile can be very complex. And this is an example from Professor Neil Davidson's group. They show they can produce a laser beam, and then it is a portrait of Newton. Okay, they can get any spatial profile you wish. And finally, we also did a spatial coherence engineering, showing we can tune the spatial coherence of a laser so that we can get a speckle-free imaging or holography. So this basically shows you that you can have really diverse spatial, spectral, temporal coherence behaviors from this complex laser. And today, I'm going to show you one example about laser instability and chaos. Okay, so soon after the invention of laser, people noticed this kind of irregular pulsation from the laser. And then after some study, they realized that this is not coming from external perturbation. This is inherent. This is actually coming from the nonlinear interaction between light field and the gain material. And also soon after that, the relation to the deterministic chaos has been established to describe the lasing dynamics. So this kind of lasing instability or chaotic lasing dynamics has been a main issue for high-power multimodal lasers because those lasers has a lot of application from like material processing, laser machining, laser surgery, and also large-scale display. And more recently, they can also use more often they also using as a pumping source to another laser. So for all this one here, we want to have a stable, high-power source. So the question is how we can suppress the instability. So let me give you one particular example of the laser. It's called a broad area edge emitting semiconductor laser. So this is usually made of gallium arsenide, and then they have a quantum well inside as a gain material. And then the light is, current is injected from the top, and then so they can pump this quantum well, emit light. And then the cavity is formed by cleaving this two-end facet. When you cleave it, you can generate this kind of planar mirror. Light is bouncing back and forth between these two. That is a laser cavity. Okay. So typically for the those broad area to high power, they make it this stripe. This stripe geometry has a width usually typically 50 to 100 micron, and the length is about 1 millimeter. So it supports many longitudinal mode and also transverse mode. So now let's try to see what happens for the emission. So here shows the emission intensity across the end facet here as function of time. So you clearly see that you see the filaments here. And also, also you see that this filaments is changing in time. So we have this kind of spatial temporal instability. And this actually result from modulation instability. So let me try to explain more in detail. So as I said, for this kind of cavity, which we call the Fabry-Perot cavity, has two planar mirrors. Because the cavity length is much larger than the width, the light is propagating predominantly along the cavity axis. So that means the k vector along the cavity axis is much larger than the transverse k vector. And then if you consider the transverse wavelength, which is inverse of this transverse k vector, is much larger than the wavelength. So typically on the order of a few micron or maybe even 10 micron. So this will introduce intensity modulation on such a long scale. So then what happens is that if we have intensity, peaked at some location, then what happens is that it's going to deplete the gain or deplete the carriers through stimuli emission process. So we call this a spatial Hall burning, meaning you burn a hole in the gain material due to this carrier density is going down. And then from the Kramers-Kronig relation, we find out that the local, the refract index will increase in this quantum well. And that form a lens. And this lens can focusing light, okay? So that focusing will form a filament. And this filament actually is not stable. Why? Because the gain is already depleted inside the filament, but outside the filament there's gain. So therefore this filament tend to move around, and that causing this kind of instability in space and time. So that is the problem for this kind of a high power laser. So how we can get rid of it? To have such a narrow like a filament, you need many transverse spatial frequency. So one way is to make to reduce the transverse frequency. For example, there's only fundamental mode is supported. So then try to remove this kind of filaments. So that is actually has been a method developed over the last 20 years. Try to stabilize the multimodal laser by using either optical feedback or external injection, or even recently using PT symmetric system. All this method, the goal is try to reduce the number of lasing mode to achieve the single transverse mode lasing. Okay, so I try using this to stabilize the laser. But the problem is a single mode lasing is fundamentally incompatible with high power operation. Because if you want to do high power operation, you need a lot of gain material, and it tends to have a larger cavity, tends to support many modes. They will all want to lase. So therefore, all these methods will only be successful up to a certain pump power. When you go even higher above it, then you have many more lasing again, then this instability will come back. So that is an issue. So now what is our goal? Our goal is we try to suppress this spatial temporal instability while maintaining multimodal lasing. Okay? Because if we can find a solution to have multimodal lasing but stable, and then this will be compatible with high power operation, and this will be useful for many applications. So now the question is, how can we do that? Okay? So our approach is try to control this nonlinear light-matter interactions in a broad area laser by tailoring cavity geometry. Okay? By tailoring cavity geometry, we want to, in other words, we want to using the cavity geometry as a way to control the nonlinear light-matter interaction. So now, what kind of cavity geometry can we have? So there are two types of cavities depending on the ray dynamics. One we call the integrable, for example, like this kind of rectangle, or a chaotic one, like this stadium. So let's consider for the first one, an integral system. If we start with two rays, these two rays just have a slight difference in the direction of propagation at the beginning. Then after multiple bounces from the cavity boundaries, you see their distance will increase linearly with the propagation time. So we call this as linear divergence. Okay, that's an integrable system. Now, if I have a chaotic a cavity like this stadium shape, now if we have two waves that initially only slightly shift in position, after a few bounces, you see that they really stay far away. So in other words, their distance is grow exponentially with the propagation time. So we call this exponential divergence. So this is a chaotic cavity in terms of the ray dynamics. So typically for laser, we want to using an integrable system. It is regular, so it is more easy to control. So that's how we try to design the lasers, right? So what is our goal is we try to using chaotic cavities to suppress the laser instability. I don't know, some of you may have heard of this term is fighting fire with fire. If you want to stop a big fire in forest, what you do, you start another fire. So we'll try to fight a laser chaos with wave chaos. In other words, we try to suppress the laser instability using a cavity with chaotic ray dynamics. Now let's try to see whether we can do that. Why the chaotic cavity can suppress the laser instability. So we consider a particular cavity shape. There's many different shape for chaotic ray dynamics. So let's consider this one is a circle, two-dimensional cavity. Then we just cut part of it. Okay, this shape like a D, like the letter D. So we call it a D-shaped cavity. Okay, so this is a chaotic cavity. If you start with a ray, you see that this single ray trajectory will spread over an entire cavity. Okay, now. Of course, this chaotic or not, we talk about is for ray dynamics, right? If you consider the wave optics, there's no such kind of chaos because you're just solving the wave equations, find the resonant modes, so you don't have really chaos there. But what happened is that this kind of underlying ray dynamics, if it's chaotic, is going to affect the spatial structure of the cavity resonant mode. So here shows one cavity resonant mode in this D-shaped cavity. You see that first of all, this is spread almost over entire cavities. And then if we do the spatial, this is a numerical simulation, so we can do spatial Fourier transform of this field. We can see that you actually have the K vector in all directions. So that means you have the ray propagating inside this one, have light propagating inside the cavity in all directions. Okay, it's more like isotropic. So in this case, all these waves propagating in all directions, they are going to interfere. So when they interfere, they're going to form this kind of fine grains on the scale of wavelengths. So this we usually call the speckle. So if the intensity variation is on the wavelength scale, when they deplete the gain, they burn the hole or they deplete gain on the wavelength scale, very small. So therefore, they change the local refractive index. Also, they increase it, but also on a very small scale. It is also on the wavelength scale. So therefore, there's no lens. We cannot form a lens here. So if there's no lens, there's no focusing, and then there's no filament, and there's no instability. Okay, so that's basically what we try to use in this kind of chaotic cavity, this fine-grained spatial structure of the cavity mode to suppress the nonlinear process that can form a filament, so we can suppress the instability. So let's try to see whether this would work experimentally. So we actually got a commercial semiconductor quantum well laser wafer. Basically, you have a gallium arsenide quantum well embedded in this aluminum gallium arsenide. And then we do this photolithography and reactive ion etching to make this D-shaped cavity. The radius here is about 100 micron. And then we deposit the metal on the top and the bottom for electron injection, so we can have this electro pumping. Okay. Then on the same wafer, we also fabricated the standard regular cavity laser, this kind of fibroperol type cavities, try to compare. So for fibroperol cavities, again, we can see this. This is the output intensity. As this vertical axis is the spatial coordinates. The horizontal axis is the time. Clearly, we see the filaments here. Okay, and then if we do the temporal Fourier transform of the intensity, we can see this oscillation up to 1 gigahertz. So this is like an oscillation on the order of, say, nanosecond scale. And this is actually coming from this kind of filamentation and the instability. However, if we see a D cavity here, okay, now we see this output intensity is much more stable in time. Okay, we no longer see this kind of oscillations. And then if we do this RF spectrum, we don't see any oscillation frequencies here. So that means things like the output is stable. But then you can say, well, is this filaments? or not, because this seems to be like a filament. But actually, what we figure out, this is not filaments, okay? So what happened is that this is from numerical calculation. We calculated the spatial profile of all the lasing modes, and you see that they are more or less homogeneous inside the system, and even along this straight segment, the intensity is almost homogeneous. However, when you see the output is not homogeneous. Why is that? Because near the center of the straight segment, the light will incident at an angle larger than the critical angle for total internal reflection for those long-lived modes, which can laze, eventually. So therefore, light cannot record here. They can only record from low, meaning those positions where the incident angle is larger than the critical angle for total internal reflection, smaller than the total than critical angle for total. So then you can record. So therefore, this blue curve is experimental measurement. The red curve is numerical simulation. You see that fits very well. So that means the output profile is determined by the internal ray dynamics for those high Q modes. So that's okay. That's a good news. So we can really using this chaotic cavity to stabilize to really stabilize the lasing dynamics. Okay, and but now the next question we say that that's great, but there's a problem for practical application. So what's that? If we do this in plane, like this is a edge emitting, right? They used to emitting only in one direction. Now for this one here, because it's a chaotic shape, light is probably in all directions inside the cavity, so the output is also in all directions. Okay, so now if you want to collect the light, using some particular fibers, then this collection efficiency will be very low. So this will be issue for practical application. So now the question is, can we get directional emission, but also suppress the lasing instability? So now we want to have both, okay? So now we have to say, go back to the planar cavity we had at the beginning. So there, because light is bouncing back and forth between these two mirrors, so we have directional emission, but it is unstable. So now how we can make the laser stable but still have directional emission? We try to curve the two end mirrors. Because by curving these two end mirrors, we increase the angular range of ray propagation or light propagation within this cavity. So that will supporting the high order transverse mode. So high order transverse mode meaning the mode has many intensity maximum along the transverse direction. So in other words, they have a larger transverse K vector. So that means the transverse wavelengths will be smaller. If this transverse wavelengths will be small enough so that you cannot form a lens, for self-focusing, then we can suppress the instability. So therefore, our goal is try to minimize this kind of transverse wavelengths to suppressing the self-focusing effect. So to do that, what we do is we try to optimize the curvature of these two end mirrors. So basically, if we fix the cavity length and also the width, then we just changing the radius of curvature. We can express this cavity shape using the parameter G. People call that the stability parameter, which is related to the length of this cavity and also the radius of curvature of this mirror. So we basically try to numerically simulate the thing to see where is the optimum G we can get the smallest transverse wavelengths. So now let's try to see a few examples of the cavity shape. The first one is a planar cavity. So if we consider a transverse mode, the number is, the transverse order is m is equal to 5. We have 5 intensity maximum, but they all spread over the entire entire mirror here, right? There's no lateral confinement here. Now if we gradually curve the end mirror, now we have lateral confinement. So for example, here we show confocal. That means that if, so the focal point for one mirror, it is at the other mirror. So that's called confocal. So in this case here, when G equal to 0, we can see we have a good confinement here. Okay, then the transverse wavelengths will be smaller. Now if we further move to G equal to -1, we call it concentric. You see that these two mirrors, their center, actually it is same here. So they focus light to the center here. So now you see that at the center, the beam width is smallest. So the transverse wavelength is smallest here. So now if we plot the, at the center, the wavelength, transverse wavelength as a function of g, you see it's keep going down as we reduce g. But if you consider at the, the end, at the end mirror, for this, concentric, actually the wavelength is larger because it's spreading out. So actually the minimum, wavelength is at the center, g equal to 0. That's when we consider the wavelength at the end mirror. So if we average this transverse wavelength over all axial, positions, we find what is a minimum average wavelength. That is actually at this g equal to minus 0.7. That is we call a near concentric. So that seems to be a sweet spot where we can have, smallest transverse wavelengths. But this is for one particular transverse mode. Now we try to do this for all different order of transverse mode. Then we find for different transverse mode, we always have this, minimum transverse wavelengths at this, near concentric position. Of course, if we go to higher transverse mode, the transverse wavelengths will be smaller. So that means if we really want to minimize the transverse wavelengths, we also want to have many high-order transverse mode lasing. So what does that mean? That means that we want to have many high-order transverse mode that has long lifetime, high quality factor, and a low lasing threshold. So we calculated the number of high Q modes in the small cavity for different G. So we find out, to our surprise, is that actually the maximum number of high-order transverse mode, we want a high Q transverse mode, is maximum at the near concentric too. It seems this is also good to have a really high Q, transverse mode. So why is that? So if we consider for concentric cavities, the leakage is mostly coming from the, because the light is spreading over the end facet, it's coming from this diffraction, from this two end. So if you go to higher order modes, this is getting even leakage is higher, so this decay very quickly with the order of transverse mode. Now if we go to, confocal, the confinement is better, so we don't have this diffraction loss at the end of the mirror. But the problem is that the incident light, has an angle, to the mirror is away from 0. And this is we consider TE, transverse electric polarized mode, because for quantum well, TE mode usually lays because they have a high gain. So for TE mode, if your incident angle is deviated from the normal incidence, we know the reflectivity will going down. So that's why for this confocal, they also decreases as go to higher order, higher transverse mode. Finally, the best is near concentric, because first it is stay away from the edge of the mirror, so there is a less diffraction loss. Secondly, the angle of incidence to the mirror is almost normal, so it's the highest reflectivity for TE polarized light. That's why we have the most, number of high Q transverse mode for this near concentric. And this will be very important, I'll show you later, okay? So, but that's not enough. If you have a lot of high Q transverse mode, that doesn't mean they're all going to lace, even though they have low lasing threshold, because they're going to compete for gain. So we need to consider their nonlinear, interaction with the gain material to see how many modes at the end will lace. So here the red curve shows we simulate this number of lasing modes by taking into account a nonlinear, competition for gain for all this, transverse mode. And again, we find a near concentric, this kind of, mode competition is not sufficient to suppress, many mode from lasing. So we still have a lot of high order transverse mode can lace, okay? So that is what we want. Okay, so with all this design, we move to the experiments. Yes?
Have you tried also other shapes instead of sections of a circle, like, for example, parts of a parabola or parts of an ellipse?
Yeah, so the question is whether we can try any other shapes rather than just this one. We tried many shapes. I wouldn't say, so the question is whether this is the best shape. I wouldn't say this is a global maximum, but for the shapes we have tried, this is the, seems to be the best one. But I wouldn't say this is the best, yeah, okay. Yeah, we tried many different shapes. Okay. So now experimentally, okay, good. So if any questions, just please stop me anytime, okay? So now what we do is we do experiments. We basically, we fabricate this kind of cavities, near concentric cavities in a commercial gallium arsenide quantum well laser. And then we basically shape this, the top metal contact to match the spatial profile of the high order transverse mode so that they have enough gain to laze, okay? So that's why we try to maximize the number of lasing modes. So you can see that now the cavity size is about 10 times larger than what we do in numerical simulation, so that we can have also many more modes here. So now let's see, we also try to fabricate a slightly different shape. So first I'll show you this shape. It is, we call it concentric. Sorry, concentric here. So basically you can see that for this case here, if we try to see that this is an emission as a function of the space and the time, we still see, we don't see a lot of filaments, but we still see a little bit of filaments here. And then if we do the Fourier transform, we still see some weak oscillation frequencies there. So it is getting stable, but it's not completely stable. But now if we do near concentric cavities, now you don't see any oscillation anymore. Okay, so this has become completely stable to get rid of this, filaments. Now, if you see how much difference in the cavity shape, I plot this, green dot, just like a concentric to near concentric. It's a very small change. So that means very small change of the cavity shape can really change the lasing dynamics. Yes.
Do we have the asymmetric emission line for the concentric shape?
Yes. So the question is, do we have should this emission should be symmetric with regard to the center? In principle, yes. But in reality, because we have fabrication imperfections, we have the defects, we never get anything symmetric. Okay. So, but I also want to say that this kind of stable things is also robust against the fabrication errors. If you have all this kind of surface, defects or something here, it is still working very stable. Yeah. Good. Yes. Yes, yes. So the question is why this shape is like a bow tie shape. Because this one shows we have this high Q mode spatial profile. The mode profile like this. So we want to match this metal contact with this one here. So when we have the maximum overlap with injected current with this high order transverse mode, so then they can laze. If you do just a flat ones, then you have more overlapping with a low order transverse mode rather than with high order transverse mode. Yes. Any other questions? Good questions. Okay. At least you're awake. Okay. Good. So okay. So now we say okay. Now we can stabilize that. We can still get the directional emission. So that seems we reach our goal there. So let me try to summarize the first part of my talk. Basically, I show you that we can control the nonlinear lasing dynamics by tuning the cavity geometry. So what do we really do? By changing the cavity geometry, we're changing the spatial structure and the characteristic length scale of the passive cavity modes. By changing that, we can control how they interact nonlinearly with the gain material. And using that, we can control the nonlinear lasing dynamics. So we are trying to, by control the linear properties of the cavity modes, try to control their nonlinear interactions, okay? Because linear is much easier to control compared to people try to do injections or doing like, say, feedback. That one, you need a very fine parameter tuning. Here, we don't need such a fine parameter tuning. As long as we have this kind of cavities, it is stable. If you have different temperatures, if temperature drifting or whatever drifting is here, that's still pretty robust. Okay. So using that, we show that we can really disrupt this coherent nonlinear process that leads to the filamentation and the instability. So this is just for one particular example for semiconductor laser. And this actually approach can be applied to other type of lasers. For example, broad area vertical vertical cavity surface emitting lasers that has a large area, and we can control the cross-section shape. And also for high-power fiber laser and amplifiers, they also have instability issue. We can try to control the cross-section shape, try to control the lasing mode profile, and try to control their nonlinear interaction with the gain material to control their spatial temporal dynamics. Okay, so we have been working on those things here. I will not have time to go through that. I think because I want to talk about one application, but before that, I want to stop here for a second to see whether there's any further question to the first part of my talk. Any more questions? Yes?
I'm not sure I got exactly the one point. It's the fact that when you have the rectangular cavity, you want to avoid the spatial distribution that might induce limitation and so on. Then you showed us the chaotic cavity, and you have not this problem. Then you went back to a semi-irregular cavity, which is not chaotic.
Yeah.
And where you see that the wave indeed focuses at some very bright spots. So why don't you have limitation in this case? This is not the point. I'm not sure I got it.
Okay, sure. So the question is that, for chaotic cavity, we say we can suppress the instability. But now, when we go to this one here, which is a directional one, how we can still suppress it? Chaotic cavity definitely can suppress instability. But we ask our question is really chaos is needed to suppress the instability? So if you see what we are doing there is we try to change the length scale of this intensity variation for the lasing modes, and that actually suppresses instability. So that means if we go back to this kind of structures, if we curve the end mirrors, we can reduce the length scale, this transverse wavelength scale. Even we don't get into wavelength scale, if we make it small enough so that they cannot form a length anymore, then we can still stop instability. And what we can gain is the directionality. Because the speckle grain is coming from light going from all directions, they interfere, give you wavelength scale. That's great, that could be very stable. Of course, for vertical cavity surface emitting laser, that's perfect, because you emit in this way, you don't care the isotropic emission in plane. But for edge emitting, I do want something directional. So that's why we learned from that chaos that we learned is we just need to change the length scale of the cavity modes to small enough to suppress the lensing or the self-focusing. Yes, good. Any other questions? Okay. All right, so if not, I'll move to applications. Okay, of course, this also has applications, but I want to talk about the one new applications. Well, anyone has a new one? So random number generation. So I think we all know that we use a lot of random number these days. So basically for information security, for cryptography, even not for that, for like say a stochastic modeling, for quantum simulation, we also need we need a large amount of high quality random numbers. So in terms of random number generation, what are the key parameters we care? Quality of the random number, and also the speed of generation, the power efficiency, and also the scalability. Okay, so typical the random number we are using these days is a pseudo-random number that is actually generated by using a random seed into a deterministic algorithm. That gives us a pseudo-random number. It's not really a true random number. So therefore, even though this approach, it is easy to implement and cost-effective, it is actually vulnerable to attack. Because if you know part of the random seed or you know some of the deterministic algorithm, then you can predict what is a random number will be generated. So a true random number can be generated by sampling the stochastic physical process. Okay? For example, thermal noise, radioactive decay, electronic jittering, and quantum fluctuation, and many more. But most of this process is relatively slow. So that means your random number generation rate is not so high. So one way to really to have a high-speed random number generation is using a semiconductor laser with chaotic dynamics. So basically, this is what people have shown, a long time ago, is that you use a single mode laser diode, and then the output, you put a mirror, you get a little bit of feedback, and that can introduce this kind of chaotic lasing dynamics if you get the right amount of, the feedback. And then this fluctuation is actually can be sampled and then to generate a random number. And this, this actually fluctuation is on the order of, sub-nanosecond. That's determined by the, this response time of the gain material. So that will actually, the random bit generation rate is about several hundred, gigabits per second. And that's really very high, but that is limited because that's limited by the time scale for the light-matter interaction. So it's very hard to further increase it if you're still using this kind of process. So another way to really increase the one is to do parallel random bit generation, meaning that if we make a broad area semiconductor laser, then if if we have the filaments, we have instabilities. Now you see this intensity at different spatial locations, if they're all fluctuating here, right? So if the fluctuation was independent of each other, then you can just sample different positions to get different random bit streams simultaneously. So this can also increase the random bit generation rate. But unfortunately, they are not uncorrelated with each other. So here shows the spatial temporal correlation function of this emission intensity pattern. So we clearly see this is basically the time delay, this is spacing. Clearly we see long-range spatial temporal correlation. And this will degrade the random bit quality that we get. So now the point is we need to get rid of this kind of long-range correlations. Okay, so this long-range correlation actually is coming from this kind of filaments, because so what we just show you before is we can get rid of the filaments, right? By curving this this end mirrors here, we can really get rid of the filaments. And now if you see the spatial temporal intensity correlation function, there's no longer long-range spatial or temporal correlation anymore. So that seems to be great. No, we don't have correlated, this kind of random bits. But then the problem is, before we have this filaments give us a random fluctuation, then you can generate random bits. Now I get rid of these instabilities. Where do I get the random bits, right? Where do I get the fluctuations? So you see this time scale is 5 nanosecond. Now if I zoom in to 500 picosecond, you see that this is, even though it seems to be quiet, there's no this oscillation on the sub-nanosecond scale, actually there's some oscillation much faster. That is showing here, we call the spatial temporal speckle. So why is that? Because as I said, we try to maximize the number of transverse lasing mode. It's a few hundred transverse mode can laze. They have different spatial profile and different frequency, and we also have many longitudinal mode. They also have different frequency. They interfere. When they interfere, in space and time, they are going to generate very fast intensity fluctuation in space and time. That's what we call the speckle. And this kind of speckle, you can see that if you see that for this dashed line, we can see this intensity, oscillate very fast. So if we can sample, basically this intensity fluctuation, and then we can using that to generate random number. And the one good thing is that because we have the spontaneous emission, okay, so the spontaneous emission will keep randomize the phase between all these different lasing modes. So therefore, the interference pattern will unpredictable and also non-reproducible. Okay, so that means you cannot get the same pattern again because of this spontaneous emission noise. Keep randomize the relative phase between all these lasing modes. So now the question, you say, okay, great. Now we can just, maybe try to, sample different spatial locations, get many different, random bit streams. But how close can we sample? That's again depend on the spatial correlation width. So the spatial correlation width here basically showing that is about 1.5 micron. So that means that we can, we can make a, we can sample spatially just like about 2 micron, they'll be uncorrelated. And our end facet is about, like say, a few hundred micron. So we have many channels. And then you can say for a single position, how fast I can sample, for a single position in time domain, how fast, that's actually determined by the temporal correlation, width. Meaning how fast, you can sample these things before you get uncorrelated bits. So that's basically here shows it's about 2.8 picosecond, Okay, so that means we can really sample very fast. But I have to say that they both, these numbers determined by actually the detection, our detection system. In principle, this actually the spatial correlation width is smaller than this, and the temporal correlation is also shorter than this, but we just cannot detect. Okay, so that is our detection limitation. So this short, correlation time, meaning we can really sample very fast. So if we see this, intensity Fourier transform, we call the RF spectrum, you see it is very broad. Okay, so this is the RF spectrum. For 80% the bandwidth, meaning the bandwidth contains 80% of RF power, is about 181 gigahertz. And this is, actually limited again by our detection, bandwidth, our detector bandwidth. When we do numerical simulation, we actually find out that the bandwidth is about almost 500 gigahertz. And this is limited by the line width of our laser emission spectrum. So that's basically, this bandwidth is order of magnitude higher than what people can achieve with this chaotic lasing dynamics. That's why we can generate much faster random numbers using this approach. So it's not only we need them to be broad, we also want this RF spectrum to be smooth or dense. So this is because we really maximize the number of transverse lasing mode. So we do a numerical simulation here. If we see that we have only one transverse lasing mode, but many longitudinal mode lasing, you see the RF spectrum have these peaks. That's corresponding to the frequency of the longitudinal mode. We call the free spectral range. As we increase the number of transverse modes, now we see additional peaks in the RF spectrum because the additional transverse mode have different frequencies. When they beat, they generate additional peaks. Now, if we can go to 200 mode lasing, like what we have experimentally, transverse mode, you have so many beat nodes, okay? And then they all merge together, form really like a dense RF spectrum. And this is important for random number generation because you want to have many frequencies that are incommensurate with each other. So therefore, this interference pattern will not repeat itself. Or in other words, they give you the maximum enthalpy. So with that, we say, okay, now let's try to see whether we can get the random bits. So this for a single spatial channel, what we're using, this is the intensity, part of intensity trace. You see it's much larger than the background. We just make sure that our random number is not generated from this noise of our photodetector. So you can see it's much higher, and then the sampling time is 1.46 picosecond. That gives us the sampling rate about 683 gigas sample per second. But this intensity pattern we know for speckle, it is really statistics. So that's not good. So we're actually using the differential intensity, meaning have the subtract intensity sample at different time to get a symmetric probability density functions. Okay, and then we digitize that to 6 bits by dividing this this intensity range to 64 beams, and each beam size is larger than the width of the differential noise. Again, we want to make sure the random bits not coming from noise. Okay. So with that, out of the 6 bits, we take 3 least significant bits, okay, for this random bit generation, and corresponding to 8 different, combinations, and they all have almost the same probability. So there's very little bias here. So, so then we can see that for a single channel, this is a single channel, the bit generation rate is about 2 terabit per second. That's already 2 times higher than the fastest physical random bit generator that has been reported today. And this is for a single channel. That's because we have a very fast temporal process, using this kind of beating. But we have many channels. So if we using many, so here we set that the channel spacing is 1 micron. Then we do an XOR of 2 different spatial channels to remove residue bias. So at the end, we got 127 parallel bit streams simultaneously. Again, this is limited by the field of view of our photo detection system. But in any case, even with that, we try to calculate whether the different bits, they are uncorrelated or not. So we calculate the mutual information from those kind of random bit streams from the same cavity, and we find out that it is equal to the mutual information of the random bits we got from different cavities. So that means they are really uncorrelated. Okay, so with that, we got the total random bit generation rate of 254 terabits per second, and that is 2 orders of magnitude higher than the state of art. Okay, so now to check the quality of the random bits, we actually did this NIST test. We also did a die-hard test. There are many statistical tests. So here shows one of one channel. For NIST test, it contains 15 different statistical tests. Altogether, there's tests also have subtests. Altogether, 188 subtests. So here shows the one channel that pass. To do this test, we need to have 1,000 sequences. Each one contains 1 megabit. So altogether, 1 gigabit per channel to do this test. And then here shows it actually passed all tests here. But for out of 127 channels, 85 passed all the tests. So the pass rate is 75%. This is a statistical test. The upper limit for the pass is 80%. So this pass rate, it is comparable to the other physical random bit generators. So it is within the acceptable range for reliable physical random bit generation. So with that, I want to summarize the second part of my talk. I basically show you one application of the complex laser. By really removing the laser instability, we can utilize this kind of spatial temporal interference of many lasing modes as a new mechanism for massive parallel random bit generation. And we actually achieve a total bit rate of 254 terabit per second. As I said, this is a 2 orders of magnitude higher than the state-of-art record with the offline post-processing. This number, as I said, is determined currently by our detection system. In principle, from our numerical simulation, this laser can give us another factor of 10 more this random bit rate. So we're supposed to get a 2 petabit per second. But we just cannot get there, right now, because of the limitation of our photo detection. So right now, for this proof of concept demonstration, we measure this, this emission from the laser using a street camera, off chip. Eventually, we need to integrate all these photo detectors on chip with the laser to make a compact parallel random bit generator. And this one is actually, it is robust, okay? As I said, against the fabrication imperfections, temperature drift, and also it is energy efficient because the power per channel, it is close to 1 milliwatt, and that's a lot. How about we can even get even more channels compared to this? So we can go back to what I just told you earlier, 2D chaotic microcalculator laser. At that time, I said this is not good because for edge emitting, the light go in all directions, right? So that's not good. But for random number generation, you can just integrate all the detectors around your, around your lasers. So in this case, we actually can have many more, spatial modes, and we can get maybe many more channels. And finally, we can also try 3-dimensional random laser. And that really that's going to have a lot more spatial modes that can further increase the, the number of parallel channels we can achieve for this random bit generation. So there's still many more, room we can improve. So with that, I think that's become red. So I'll stop here. So let me try to acknowledge all the people who have done the work. Particular for the, the first part is my former postdoc Stefan Bittner. The second part, the random number generation, my student Kwang Dao Kim, they did the most of the work. And we also have help from Hassan Yilmaz. We worked with Nanyang Technological University Professor Qijie Wang and his student, a postdoc for sample fabrication, and also Professor Aldwin Hatz and his postdoc students for the, for this numerical simulation. Finally, I thank the funding agency and also your attention.